Standing in for Josephine Eller. She is on a collaborative research project in Berkeley National Lab right now, working with synchrotron lights. So she's working for me. So I'm here and can enjoy the seminar. So I know usually there are maybe announcements. That's a chance to voice your statement. Anything up? Anything you want to announce? All right, then we can go straight to the seminar. So it was a great pleasure to welcome David McGee from MIT here for today's seminar, Drivers and Impacts of Saharan Dust Emissions Since the Last Glacial Maximum. A little bit to David's background. So he got his BA in geology in Carleton College, Minnesota. Then he got an MA in teaching with a certification in environmental education in Chatham College. Did I say that right? Yeah, okay, in Pittsburgh. Then he went to Tulane University to get his MS degree in Earth and Environmental Studies, and then followed up with a PhD at Columbia University here in New York. Then he did postdoctoral studies. He received the very prestigious NOAA Climate and Global Change postdoctoral fellowship, and he did his postdoctoral studies at the University of Minnesota with joint appointment at the Lamont Doherty Earth Observatory, which many of you are familiar with. And then since 2012, he's assistant professor at MIT and took the trip down here to tell us about his recent studies related to Saharandust, which many of us are interested in. And so, welcome, David, and take the stage.
All right, well, thank you all for being here today. It's been a great pleasure to be able to visit Stony Brook for the first time. Am I loud enough to be heard everywhere, but not too loud? Okay. So I'm going to be talking about some of our work trying to understand how the Saharan dust plume has changed over the last roughly 20,000 years. This is work with Peter Domenical, who's been working on this problem for about 20 years now, 25 years now, and some other colleagues at Lamont, at NIOS in the Netherlands, Louisa Bratt-Miller at Macalester College, and then a couple of graduate students at MIT who have sort of started to take the lead since I arrived there. So the Sahara Desert is, of course, the largest source of mineral dust to the world's atmosphere. It produces a dust plume that extends not just within the desert, but out over the tropical Atlantic Ocean. And it has a characteristic seasonality because of the north-south migration of the intertropical convergence zone and the associated easterly winds. You get more purely east-west transport of the dust during northern hemisphere summer, and dust transported in a kind of a southwestern direction during northern hemisphere winter. I should say that what's shown here as a satellite-based estimate of the dust loading in the atmosphere, there's some contamination by biomass burning that's down here. These are not dust sources shown. But these up here in the heart of the Sahara are these dust-producing hot spots. And then you can see the dust heading out, mostly dust, heading out over the North Tropical Atlantic in Northern Hemisphere summer. So we'd like to understand how this kind of basic feature of the modern climate has changed in the past. And there are a couple of reasons for doing this. One is that dust we can treat dust as sort of a passive recorder of what's going on at the land surface and in the atmosphere. In order to have dust emitted from a place, of course, you have to have low vegetation density, you have to have a supply of fine particles, and you have to have strong enough winds to uplift that dust and then transport it. And so it can tell us about all those sorts of things in a kind of an integrated way. And then, of course, as many people work on here, dust is not just a passive recorder of what's going on in climate. It actively impacts radiation, mostly by reducing the amount of radiation, the solar radiation that reaches the Earth's surface, but also indirectly through interacting with cloud formation. And the supply of micronutrients, chiefly iron, from dust to the surface ocean is also important in terms of biogeochemistry. And so if we want to understand how these things might have been different in the past, we obviously have to have some sense of how much Saharan dust emissions have changed in the past. So there's been some measurements of this over the last 50 years. This is Joe Prospero's record from Barbados, where they've had a station since the mid-60s, I believe, basically capturing on the ocean side of Barbados, capturing dust that's coming in from across the Atlantic and measuring its variability over time. You can see there's very large interannual variability, very large seasonal variability. Barbados is mostly getting dust in that summer dust plume. And also some decadal scale variability. You can see this increase from the 50s, from the 60s to the 80s, in a time that as many of you know, the sub-Saharan Africa experienced significant droughts. But anything before 1966 is essentially the realm of paleoclimate. We just don't know anything about how much dust was coming out of Africa beyond a few sort of documentary reports. Charles Darwin, sailing the Beagle through the Atlantic, reported red dust landing on his ship, but the reports are pretty much few and far between. We also know that there should be a signal out there to measure. If you go to archaeological work in North Africa and work on pollen distributions has shown that North African climate has changed profoundly, even over geologically short time periods, just say the last 10,000 years. So in this place in southwestern Egypt, if you go there today, it looks like this. But on the walls of some of the rocks there, I don't know if you can see this in the back, but there are these depictions of giraffes and people herding, large ungulates. And there's an ostrich in the lower left there. Somewhere else in this same place, there's a picture of people swimming in a swimming hole. This is sort of basic evidence that this region did not always look like it did today. But these, of course, are just, we can go out and date some, if you can find correlative deposits with these, with this rock art, you can get a sense of the snapshot of a time when it was wetter. But to get a continuous record through time, you have to go to something that's deposited continuously. So one of the ways you can do that is to go to deep ocean sediments. So this is a sediment core that was taken off the west coast of Africa. You can see it has this kind of, there's a substantial kind of brick red component to its coloring. And it's been split down the middle, and you're just getting mirror images of this PVC pipe. And it's in a region where the accumulation rate of the non-biogenic sediments, that is not carbonate, not diatoms, the opal from diatoms, but basically everything else, the mineral matter in the sediment, is dominated by wind-blown dust that gets deposited on the surface of the ocean and sinks to the bottom. So what we're trying to do is to use these sediments from along the Northwest African margin to understand how this deposition has changed in the past. So we're looking, as I mentioned, we're looking over the last 20,000 years. This is the time since the peak of the last ice age, the last glacial maximum. So what are the changes in the boundary conditions, kind of the broad perspective of Earth's climate that have changed since then, that are going to be that dust is going to be responding to? So there's basically sort of three parts of this. The first part of it is the simple fact that in the last glacial maximum it was colder, there was lower CO2, and there was more ice. And so that's reflected in this record of Antarctic temperature. So here time is going, this is a paleoclimatologist speaking, so in my world time goes this way, from 20,000 years ago to the present. So we're going from cooler to warmer temperatures in Antarctica, and global temperatures basically look very much like the same pattern. Atmospheric CO2 has been rising. It's went from low to high, and sea level went from low to high as ice sheets melted and caused sea level to rise. So I have the sea level on there just to kind of show an inverse of ice volume. So there's the last glacial maximum centered around 20,000 years ago, and here's the Holocene, the last 11,000 years. At the poles, reasonably stable temperatures. Superimposed on this are changes in interhemispheric temperature gradients. So the difference in surface temperatures between the hemispheres. So this is a compilation of about 90 paleotemperature records from around the world, done by 2 different studies that just covered slightly different time periods. But if you take those proxy-based estimates, you kind of grid them into a global or a hemispheric estimate and subtract them, this is what you get. And as you see, it looks very different from that previous record. 20,000 years ago isn't the most different time now. There are these 2 pretty pronounced perturbations during what we call deglaciation, first about 18 to 15,000 years ago, and then about 12 to 11,000 years ago. And I should say that on here, up is a warmer northern hemisphere relative to the southern hemisphere. And these were given names by paleoclimatologists and their sort of historical names. This is called Heinrich Stadial 1 or Heinrich Event 1. This is called the Younger Dryas. And these seem to be times when at least proxy records that we think tell us about the strength of the North Atlantic steep overturning circulation weakened. And then that potentially reduced the ocean's heat transport in the northern hemisphere and cooled down the northern hemisphere. And then the final part of the story of the last 20,000 years is orbital changes. So because of the precession of the Earth's axis, northern hemisphere summer was closer to the sun during the early Holocene, around 10,000 years ago. And this was an effect that was, so this is northern hemisphere summer insolation at 20 degrees north, kind of in the heart of the Sahara. You can see that there was substantially more incoming solar radiation heating up the land surface and the sea surface during northern hemisphere summer around 10,000 years ago. So the basic questions are how have dust emissions responded to these changing boundary conditions? And do we get similar answers if we go to different places? Or are dust emissions, is the Saharan dust plume kind of a spotty thing that doesn't vary coherently? And then finally, if we can get quantitative estimates for how much dust fluxes have changed in the past, were they large enough to have important climatic or biogeochemical impacts? And these are the 2 I'm going to focus on today. At the end, I'll sort of, wave my arms a little bit about whether these are important or not. But this is kind of where this work needs to head, I think. So here's another satellite-based estimate of image showing the kind of integrated strength of the dust plume and this transport out over the North Tropical Atlantic. Some of our best records of the last 20,000 years come from this ocean drilling program site that was drilled in the mid-1980s and worked up first by Peter Domenical in 2000. And here's the record of, this is total so-called terrigenous flux. This is just taking all of the mineral matter that's entering this core and calculating an accumulation rate in grams per square centimeter per 1,000 years, and assuming that it's all windblown dust. So that's an assumption that we're going to hold right now, and we'll kind of relax it in a few slides. But you can see these fairly pronounced changes, so kind of factor of 2 or maybe factor of 3 changes over the last 20,000 years. With this prominent low period from about, actually I have a laser pointer, I should use that, sorry. Prominent low period from about 11 to 5,000 years ago. These spike around 11,000 years ago, 12,000 years ago. And there was a core break right here. And then relatively high and rising fluxes over the last 5,000 years. So the question, of course, with a record like this, it's been interpreted widely and it's a very interesting record, but this is just one site. And the changes could equally be because you're changing the source function, how much dust is coming out of North Africa, but you could also get changes by just moving this dust plume north and south. If you can imagine taking this dust plume and just shifting its core south a little bit, this core would record lower dust fluxes, presumably. So what our goal was to try to go to cores up and down the margin first and understand whether we could reproduce this record. Did we get records that were similar in terms of their shape and reasonable in terms of their magnitude? And so what we did is we started with a spatial array of cores, as I say here. We measured terrigenous fluxes by a method called thorium-230 normalization. So happy to talk about the methods towards the end of the talk. But the basic idea here is that thorium-230 is produced in the water column by uranium decay, and then it tags particles. And because it has a known and constant source function, thorium-230 concentrations in the sediments are inversely proportional to the accumulation rate. That is, thorium-230 comes in at a constant rate like a dye, and then it gets diluted in places with high accumulation rates and is relatively concentrated in places with low accumulation rates. We also tried to relax this assumption about all of the triginous sedimentation on the margin being windblown. And so in doing this, we took advantage of the fact that if you sample dust directly in the atmosphere, it has a characteristic grain size in this region that is actually fairly coarse. The modal grain size is something around 15 to 25 microns. And so that makes its grain size peaks substantially coarser than, say, fluvial inputs or remobilized shelf sediments that have gotten picked up by ocean currents and brought to our core site. So we did some end-member modeling to try to understand how much of our sediments are actually windblown. And then, of course, we did the spatial array. And so first I'm going to talk about these records along the African margin, and then we'll go west to the Bahamas. So here are our core sites. They span about 8 degrees of latitude, going from the northern edge of the modern dust plume down right into its core. We were supposed to go further south, but the ship's motor broke. So here are those records, and they are arranged from the north to the south, so 27 north to 19 north. And here's this record that I showed previously from ODP 658C. And so one thing that you can see here is the fact that all of them show this prominent low between about 12 and 5,000 years ago. They all have these peaks that are about 12,000 years ago, and then the cores that record the period from about 15 to 18,000 years ago also show a peak. And then there's relatively kind of similar dust fluxes to modern around 20,000 years ago, at least in the cores that record that time. And actually, we've extended these records back to about 35,000 years now. It does look like the last glacial maximum is not terribly special. So we call these periods the late Holocene. That's the last 5,000 years. The African Humid Period, the Younger Dryas Cold Period. This is called the Bowling-Allred Warm Period, and Heinrich Stadial 1. And again, I'll remind you that Younger Dryas and Heinrich Stadial 1 were those cold periods in the northern hemisphere that I pointed out earlier. So it's hard to see from where you're sitting, I'm sure, but one of the things that we see as we move south is a shift from lower dust fluxes here, so the maximum here is 0.5 gram per centimeter squared per 1,000 years, and systematically towards higher dust fluxes as you go towards the south, towards the core of the dust plume. So the maximum here is about 10 times higher, 6 grams per square centimeter per 1,000 years. And so that's consistent with the fact that as we're moving towards the core of the modern dust plume. These are the dust fluxes that we reconstruct for the last, so the average of the last 2,000 years in gram. We've shifted units now to grams per square meter per year because that's how modern atmospheric folks think about things. And here are estimates from sediment traps along the margin. Now this is an almost ridiculous comparison because these sediment traps were put out for 2 years in the 1990s, whereas these are averages of the last 2,000 years. The point here is not to expect perfect agreement, but just to say, in terms of order of magnitude and in terms of the relative change as you go from north to south, we're getting it about right. We're getting reasonable results. They're certainly not inconsistent with the fluxes we're recording, and so it provides some confidence in the methods that we're applying to look back in time. But these are dust flux records from, basically, we're looking at offshore sand dunes, or at least offshore silt accumulation. And the coarse grain sizes we're seeing in these cores suggest that the dust hasn't been transported that far. So we're probably looking at dust sources that are just along the western side of Africa, northwestern side of Africa, and it's uncertain whether these really reflect kind of an integrated signal or whether they're representative of the rest of Africa, the rest of North Africa. The other thing about this region is that in the modern world, and certainly observed in the sediment traps, the dust fluxes are associated with the winter. So strong winter surface trade winds are kind of coming in this way and driving dust accumulation in these cores. So they're probably not representative of what the summer dust plume is doing. So to understand that a little bit better, we went downwind to the Bahamas. The reason that so the Bahamas get dust during the summer from North Africa. The reason we didn't end up anywhere in here, a little bit closer to the actual dust plume, is that sedimentation rates are low enough that it's really, really hard to get records that allow you to tell the last 5,000 years from 5 to 10,000 years. So your resolution really goes down. So we went to the Bahamas, went to two cores that are basically right on top of each other in the Northwest Providence Channel. So this is a deep channel that's between the Bahama Banks, just north of Andros Island and west of, actually I don't know my Bahamas geography well enough, but north of Andros Island. The reason that we have some confidence in trying to use these sediments for understanding African dust is based upon some careful geochemical work that's been done in Bahamas soils. So the Bahamas are giant carbonate factories, and that's basically all they are. There's no local sources of non-carbonate material, essentially. And so everything that's not carbonate in the soils has to be blown in from somewhere else. And so if you go to those soils and you dissolve out the carbonate and measure what's left, you get something with the composition of these dots shown in these diagrams. So here we're looking at a ternary diagram of lanthanum, scandium, and thorium. Those are the Bahamian soils, the kind of non-carbonate fraction of them. And they're sitting right on top of this little field that's African dust and Mississippi loess. So this is windblown deposits that come from the last glacial period in North America, where there was all this glacial outwash coming from the Laurentide ice sheet. Importantly, they don't look anything like other Caribbean volcanics. And that's also true in these plots that look at the rare earth element patterns of the samples versus African dust and Mississippi loess, and then compare it against the volcanics. So we actually have a hard time distinguishing. If you look at enough elements, the soils do look more like African dust than Mississippi loess. There's something like an 80-20 relationship if you do sort of multiple linear regression. But if we're just focused on the last 10,000 years, less deposits in North America were largely stabilized. They were all vegetated over. They were really probably only active during the last glacial period of deglaciation. So as long as we focus on the last 10,000 years, we're probably pretty safe in saying that the accumulation of non-carbonate material in sediments near the Bahamas is dominantly African dust. So what does the record look like? So here, these are the radiocarbon age constraints on these two cores that are right on top of each other. And here's the dust flux. And when I say dust flux, what I'm saying is that we measured the accumulation rate of thorium-232, which is the dominant isotope of thorium. It's associated with upper continental crustal material and aluminosilicates, and not in carbonates at all. And then use the average upper continental crustal concentration of thorium, actually the concentration of thorium that's been measured in African dust, to back that out to a dust flux. And what we see are lower values than you see in the African margin, which is quite reasonable. And then we see this prominent dip from about 5 to 11,000 years ago, relatively high and rising dust fluxes over the last 5,000 years, and these peak dust fluxes during the deglaciation. So this is a familiar pattern from what we saw on the margin. I'll compare them directly in the next slide, but I just want to say really quickly that these are kind of strange sediments because they get most of their accumulation rate is much, much higher during the last 10,000 years than before, because they respond a great deal to the flooding of the Bahama Banks as sea level rises. So the record from, the record from about 11 or 12,000 years onwards is quite high resolution. It's something like, these sediments are accumulating at something like 10 centimeters per 1,000 years. But before that, they're only accumulating at something like 2 centimeters per 1,000 years. So this record is heavily smoothed and there's not a lot of age control in there because there's just not a lot of sediment accumulating. So if we compare that to one of our records from the Northwest African margin, we see this prominent dip from 5 to 11,000 years ago. Looks very much like what we see in the Bahamas. And so what I take away from this is that it's reasonable to think that we're looking at kind of a consistent story of what the African dust plume has done over the last 20,000 years, in that we see it in an proximal site that is mostly reflecting winter dust emissions. We see it in a distal site that's mostly reflecting summer dust emissions. We get essentially the same answer. There's one important difference though, oops, there we go. And that's the fact that over the last 10,000 years, the difference between, say, 6,000 years ago and more recent times is something like a factor of 5 along the Northwest African margin, and it's only about a factor of 2 on the Bahamas. And so this is probably a more representative number for how much the kind of integrated transatlantic transport of dust has changed over the last 10,000 years. So we see that there have been significant changes in how much dust is over the North Tropical Atlantic. And there are 2 questions that come to mind. One is, why is that happening? What does it tell us about climate and about what was going on in Africa? And the second is, what would be the potential impacts of this? If you think that dust is radiatively important, or if you think that phytoplankton respond to how much, or they care about how much iron is being brought in by dust, are these changes enough to make a difference? So turning to that first question, what's driving these dust flux changes? We can start by just looking at correlations. So this is our best resolved dust flux record, just turned upside down, so that inferred wetter conditions are up and inferred drier conditions or windier conditions are down. And we see a couple of things. First of all, this prominent minimum in dust corresponds to the maximum in local summer insolation. This accords with what we think we understand about monsoon circulations, in that that monsoons in a given hemisphere are strongest when you have the highest summer insolation, driving heating of the sea surface, so you have more specific humidity in the surface layer and more moist static energy. You also heat the land surface and drive this monsoon circulation more intensely. But it's not the whole story, of course. This part of the record certainly does not look like this smooth insolation curve. What it looks like much more are North Atlantic sea surface temperatures, or this balance of heating between the hemispheres. So you can see that this is a record of sea surface temperature. It's just a good example taken from just offshore of Portugal. And you see these prominent cold events during the Younger Dryas, the Heinrich Stadial 1, that correspond to these peak dust emissions from North Africa. This is also a time when you had this disruption of North Atlantic circulation. And so sort of integrating these insolation and sea surface temperature stories together is this interhemispheric temperature gradient. You can see these similarities between what the interhemispheric temperature gradient is doing and what's happening in terms of African dust. That when the northern hemisphere is warmer, you have less dust coming out of Africa. When the northern hemisphere is colder than the southern hemisphere, you have really much more intense dust emissions coming out of Africa. And this has a lot of similarities to what we see in the modern world. So just looking over the much shorter observational record of the last, say, 50, 60 years, these are North Atlantic sea surface temperature anomalies, the AMO index. So this is a colder northern hemisphere and a warmer northern hemisphere. This is rainfall in sub-Saharan Africa and or in the Sahel region. And these are North African dust emissions. So colder North Atlantic, more dust coming out. And so at least it's similar in sign. If we can't really say if the slope is the same at this point, but we can say that the sign makes sense in terms of what we've seen in the modern atmosphere. And in a way, this puts North Africa in the same class as other monsoon systems from around the world. So if you look at monsoon, this is a terrible figure for people in the back. I apologize for that, but I'll just sort of describe it here, that these proxies of northern hemisphere monsoon precipitation in the Asian monsoon region and northern South America are basically co-varying with these records of dust coming out of Africa. That is, inferred wet times are times of low dust emission, inferred dry times are times of high dust emissions. And the southern hemisphere monsoons, records from South America and now some new records from northern Australia suggest an anti-phasing. Basically, when the southern hemisphere is warmer, these monsoons are fired up. So, is it all about precipitation? Is it just that these changes are just changes in the strength of the monsoon and how far the West African monsoon is able to penetrate into the continent and bring precipitation farther north? Is it just that these times are really dry and the early Holocene is really wet? Well, certainly we know that the early Holocene is really wet. That's the time when these people were out in the middle of the Sahara drawing giraffes, and the time when we get these lake expansions and pollen showing vegetation moving into the now unvegetated parts of the Sahara. But there's probably something else going on as well, and that probably winds were co-varying with these precipitation anomalies in Africa. So shown in blue here are records from the same cores of biogenic opal accumulation. If you make the, and I could show organic carbon accumulation, but it would basically look the same. So if you make the assumption that this production of opal and organic carbon, this preservation of opal and organic carbon reflect something about their production in the surface ocean, and that their production in the surface ocean is driven by coastal upwelling, that's driven by winds, then really the only thing that dust has in common with opal production in the surface ocean, this diatom productivity, is wind strength. That is, the same winds that entrain the dust drive upwelling on the margin, which brings nutrients to the sea surface and causes these diatom plumes that then get recorded in the sediments. And as you can see throughout the last 20,000 years, and indeed throughout longer periods in some of these plots, in our cores we get these systematic covariations of the dust in red and the opal accumulation in blue, which suggests there's some sort of covariation that's going along with surface wind strength. And both of these are basically consistent with an idea where if you make the northern hemisphere colder, you enhance surface trades. This is an experiment where people, where Broccoli and co-authors, cooled the North Atlantic. You get, in these red colors, you get a reduction of precipitation in the northern hemisphere and an increase in precipitation in the southern hemisphere tropics. And then these vectors are very hard to see from where you're sitting, but they suggest a slight enhancement, at least, of the trade winds along in coastal Africa, and also winds throughout the North African continent. And then if you look at the overturning stream functions, this is for the control simulation. This is a more idealized simulation that they did. But in the control simulation, here are the Hadley cells. They're reasonably symmetric. And then when you cool down the northern hemisphere, you move the ITCZ into the southern hemisphere and greatly intensify the northern hemisphere's Hadley circulation. So if the winds in North Africa are some sort of local expression of the surface limb of the Hadley circulation, this would be sort of consistent with an overall idea where you cool down the northern hemisphere, the tropical rain belt, both the marine ITCZ and the continental monsoons move south, and you intensify the Hadley circulation and its associated winds. So there's one last piece of this puzzle that's puzzling. And actually, perhaps two are worth mentioning. One is that in this canonical record from ODP 658, you can see these, what we would call in the paleo world, abrupt changes. That is, changes that look quite rapid. And there's this rapid decrease in dust accumulation around 11,000 years ago, this rapid increase around 5,000 years ago. These increases and decreases during the deglaciation relate to very abrupt changes in northern hemisphere temperatures. And so these abrupt changes might just be a linear response to an abrupt driver. This abrupt increase here in about 5,000 years ago is a little bit harder to explain though. In the northern hemisphere, sea surface temperatures and overall northern hemisphere temperatures aren't really changing over that time. The only thing that's changing is you're getting this gradual decrease in northern hemisphere summer insolation. And so this has been pointed to as some kind of an abrupt response or nonlinear response to a gradual change in forcing. And one of the things that we wanted to ask was, is this record representative? Before we go, so a lot of models have then gone on to try to understand how a monsoon reacts nonlinearly to a gradual change in forcing. And it's kind of a basic question. Do monsoons react to changes in forcing like a thermostat where you just turn a little bit and it gets a little bit more or a little bit less? Or do they react more like a canoe where you can get to some tipping point and then you get into just a fundamentally different regime that's hard to get out of? So we wanted to ask, well, are our records consistent or inconsistent? Can we demonstrate that they're inconsistent with this abrupt rise at around 5,000 years ago? Well, one of the things you have to take into account is bioturbation, is the stirring of marine sediments by worms and other creatures that live on the seafloor. And so, if we had an abrupt change, in this case from red sediment to yellow sediment, it might look like this without bioturbation if we had no oxygen in the seafloor. But in an oxygenated seafloor, benthic creatures are going to mix that signal. And so we have to account for that, and it's definitely going to smooth our record and to decrease our ability to see abrupt changes. And as you probably noticed, though the 658C record looks kind of jumpy, there's kind of these step changes, our records are less step-like, and they show more gradual changes here. And this has to do with the accumulation rates. So the ODP 658 is accumulating at something like 20 centimeters per 1,000 years. Our cores are half that or less. And so even though these benthic creatures might be doing the same thing at all 4 core sites, if there's lower accumulation rates, if they're mixing, say, 5 to 10 centimeters at the seafloor, they're mixing more in time, even if it's the same in space. And so to try to quantitatively model this, we use a very, very simple bioturbation model, just assuming homogenization of the upper 5 centimeters of sediments. And we've started by looking at a climate change that we think was abrupt, and a lot of other proxy records suggest it was abrupt. That is the end of the Younger Dryas, this warming of the northern hemisphere at about 11.7 thousand years ago. This is well constrained from ice cores. And basically, I won't dwell on this too much, but basically took our records, which are in gray here, from the 4 different cores, and then just asked what sort of input function do you need if you bioturbate it to get the observed output function. So if we input this dotted line step change here, we get this smooth red line that looks very much like our data. And basically all 4 cores are consistent with some sort of a step-like decrease in dust fluxes at the end of the Younger Dryas. And if you take a weighted average of the timing of that transition, you get something around 11.8 plus or minus 0.2 thousand years, which agrees with the independent estimate of the end of the Younger Dryas. So it suggests that using this method, we can get a sense of at least whether our results are inconsistent with an abrupt change, and can get an independent estimate of that, or get a weighted mean estimate of the timing of a change. And so we did this at the end of the African Humid Period, and basically got the same result, that the gradual changes we see in the cores are consistent with step-like increases in dust accumulation rate in the cores, and they've just been bioturbated different amounts. So you see the pretty good agreement between the red line, that's the output signal from this bioturbation model, and our data here. And taking all these all together, we get perhaps a better estimate for what time the end of the African Humid Period was. And the reason that you need this modeling to get this timing is that, as you can see, bioturbation tends to take an input signal that happened at a given time and displace it older in the core. It displaces it down in the core. So you would if you just took the core's data at face value, you would not only underestimate the abruptness, but you would overestimate the age. So is this abrupt end of the African humid period only seen in dust? Dust is kind of a nonlinear thing. You dry out an area, it's not going to be a dust source, not going to be a dust source, not going to be a dust source, and then it gets dry enough, and suddenly it's a big dust source. So you can imagine that dust has some nonlinearities of its own that don't really reflect drying of Africa. Maybe Africa was drying on the whole linearly, and dust just responded non-linearly. Well, there are a couple of records that suggest that this abrupt change was reasonably widespread. So this is a record of sea surface salinity, reflecting how much water is coming out of the Niger River and into the Gulf of Guinea. And so you can see this low sea surface salinity during the African humid period, consistent with a lot of water coming out of the river. And then there's this step down before subsequent drying that's right at 4.9 thousand years ago. If you go to East Africa, quite far away from the sites that we're looking at, you also see this step-like change towards more inferred arid conditions. This is a measure of the deuterium isotopic composition of leaf waxes preserved in lake sediments. And it's thought that this deuterium isotope composition is a sort of an integrated marker of aridity, with more positive values oriented down in this plot being drier conditions. And Just Tierney, the person who led this study, has then gone into other sites in East Africa. This is a record of leaf waxes that are accumulating in the Gulf of Aden, published last year, that also shows this step-like change. And taking her records together, she gets an age of 4,900 years ago, which is synchronous with the dust rise in West Africa. So all of this together suggests that this is a widespread change throughout North Africa at this time. We're still trying to understand the spatial extent of this change and why it happened abruptly. Some people have suggested vegetation feedbacks, that because vegetation changes the albedo of the surface and it changes moisture fluxes out of the surface, that if you have gradually decreasing vegetation, you get some sort of a step-like change in precipitation. And that's still a possibility, and it's limited by the fact that our models simply don't do vegetation that well at this point. But I also wonder whether dust might have a direct role. And I think this is the sort of thing that's easy to wave your arms about and simply just needs to be done quantitatively, now that we have reasonable quantitative estimates of how much dust emissions changed across this transition. So recent authors have suggested that this correlation that I pointed out earlier between cooler temperatures in the North Tropical Atlantic and increased dust emissions was not simply a one-way system. It wasn't simply that you had colder temperatures, you reduce precipitation, you increase wind strength, and you get this passive response of dust coming out of North Africa. That in fact, African dust acts to cool the Atlantic and perpetuate these sea surface temperature anomalies over multiple years. And one of the pieces of evidence that's pointed to for this, though is still very much work in progress, is the fact that the imprint of the estimated radiative impacts of these dust changes matches pretty well the observed sea surface temperature anomalies associated with different dust emissions. So shown in the colored contours here, the gray to white contours here, is the sea surface temperature anomalies that are associated with high dust over the last 50 years. And shown in the line contours are the estimated radiative forcing of the Saharan dust plume during these high dust years. So you can see a pretty good covariability between what the sea surface temperature is doing and what the dust radiative forcing is doing, suggesting the dust is actually feeding back on these sea surface temperature anomalies. And so one thing that I wonder about the end of the African humid period is if you had low dust and that allowed sea surface temperatures in the North Atlantic to stay warm, and then you suddenly started increasing dust, you would further cool the sea surface temperature and lead to a positive feedback that could take you to a drier and dustier climate state. Again, still driven by insulation fundamentally, but supporting a nonlinearity there. And then lastly, there seem to be important impacts of dust deposition in the North Tropical Atlantic on the biogeochemistry of the region. The suggestion is that the high iron supply to the North Tropical Atlantic supplies the iron that is necessary for nitrogen fixing phytoplankton to do their job. And so the fact that nitrogen fixers have much higher abundance in the North Tropical Atlantic compared to the South Tropical Atlantic. It's been suggested that this relates to the impact of Saharandust deposition on the North Tropical Atlantic. So the obvious question would be, 6 to 10,000 years ago, if we had only half as much dust being deposited in the North Tropical Atlantic, would this have decreased the activity of these nitrogen fixers? In particular, Nick Fallow's work that I've read suggests that there's so much iron being supplied to the North Tropical Atlantic today that a factor of 2 might not impact the core of the dust plume. But at the boundaries of this dust plume, you might get a response. Indeed, in the modern world, you can see seasonal changes in nitrogen fixation, basically in the equatorial Atlantic, where the ITCZ is migrating seasonally and bringing more dust during Northern Hemisphere winter and less dust during Northern Hemisphere summer. You see nitrogen fixers kind of turning on during Northern Hemisphere winter when they have iron around to do their work. And so you could imagine a similar response during the early Holocene. So I'm going to end there and just say that basically our results, first of all, make this basic observation, just sort of really first order observation, that it looks like we get reproducible records along the Northwest African margin and the Bahamas. And they're reproducible in terms of the magnitude of the response and the shape of the curves, but they're also quantitatively reasonable. The past dust fluxes show strong correlations with the temperature gradient between the hemispheres and proxies for trade wind strength. And they hopefully provide a starting point for estimating these climatic and biogeochemical impacts. And together with other people's work, this abrupt end of the African Humid Period about 5,000 years ago appears to be robust. It appears to be something that's worth understanding because it seems to happen in both tropical West Africa and East Africa and the Sahara at about the same time, and to be similarly abrupt in all these places. So with that, I'll end and see if there's any questions. Thank you.
Yes, the floor is open for questions.
So the Sahara Desert was covered by vegetation in about 2,000 years ago, right?
Yeah.
So my question is that, was the dust at that time covered by the vegetation the same as currently comes from the desert?
So if I'm understanding your question correctly, the areas that we think are the dominant sources of dust in the modern world were either lakes or were covered by vegetation 6 to 10,000 years ago. Not all of them, but in large part, yes. And not tropical rainforests, where we're talking grasslands or something. It seems like C4 vegetation stuff.
So you can pretty sure that the dust comes from the African nomadics covered by the desert or the vegetation.
I see. You mean during this kind of minimum dust, say here. Are you asking where does that dust come from?
Yeah.
Yeah, a good question. So that's work that needs to be done. So there's been some work done on in this core actually on the provenance of the dust, and one of the things that comes out of that is a constant epsilon neodymium basically over the last 15,000 years. Am I remembering that right, Troy? There's also some really interesting strontium isotope results that I don't really understand, but the epsilon neodymium suggests that at least in this site you're at least seeing the same neodymium signature. But downwind in the Bahamas, I mean, this is something that we're just starting to do with trace elements first, and I hope we'll move on to radiogenic isotopes.
And just to follow up or a comment, but that is quite interesting because it's about aerosol source strength and so source apportionment. And of course, if your source changes in terms of transport, it affects everything. So that's quite interesting. If your area is changed by an order of magnitude, dust supply, it will have quite a nonlinear effect of the dust transported further away.
That's right. And if you want to estimate, say, radiative properties of the dust, you pretty much have to know where it's coming from. You know, you have to know that the source was the same.
Who was John?
Yeah, so your increase in your dust loading, I mean, your decrease or your minimum is coincident, right, with the Holocene thermal maximum, but your increase actually is coincident with your methane increase around 5,000 BP, very close to that.
Huh.
But your CO2 increases starts to increase around 6,500 to 7,000 years BP. I mean, gas people and solid earth people usually don't talk to each other, but
yeah.
have you thought about that at all? Right?
No, and I'm solidly in the solid earth camp, so
so
I haven't given enough thought to that. But I should look at the methane record.
It's right there.
Okay.
At 5,000 years.
Okay. And is it, does it look like insulation, or does it look quicker than that?
It's not as abrupt as yours, but of course you're averaging, right, over the whole hemisphere and the globe. But the timing, it lines up with your increase of 5,000 years perfectly.
Oh, yeah.
So, can you comment on these very large fluctuations you have in the most recent part of the record?
Oh, these?
Yeah. Are they real, what do they represent?
They could very well be flyers. I mean, this is driven not by so the terrigenous flux is the thorium-based accumulation rate multiplied by the terrigenous percentage. And these are flyers with abnormally high thorium concentrations in these samples. So these are flyers, I think, in the mass accumulation rate, not in the concentration. We just got back from sampling some cores that we think will give us reasonably, I mean, for us, high resolution, sort of multi-decadal averages over the last 1,000 years. And so we're going to be able to kind of zoom in on this time period and understand, what was pre-industrial African dust like. We don't know that at present, with the exception of maybe one study.
And so this uncertainty is not present in the earlier record.
I don't know why Jess got these flyers here and not elsewhere. That's a good question. I haven't seen it in our data, and these data were collected by someone else, but we haven't seen like these weird excursions from kind of the long-term average.
My understanding of upwelling around northwest Africa is quite different because you have very strong wind. Actually, you don't get a high primary production.
Oh, okay.
The mixing is very strong. So you really need this kind of optimal wind range. So I don't know whether that may actually reflect.
Oh, interesting. So
it's very unusual. It's not like your typical upwelling regions.
So what drives this sweet spot?
I don't know because you don't really get very high primary production over there because it's too strong mixing.
Huh.
So the part never stays.
Oh, they're light limited?
Yeah.
Okay, wow. All right, well, so yeah, and that's definitely a naive part of this presentation. The link between the opal and productivity, is something that, and I've been looking around anyway, I'd love to talk about studies that have tracked this over, you think from the satellite era, you'd be able to combine it with reanalysis data and make an estimate of kind of what's the relationship between how much chlorophyll there is in the surface ocean, or how much you get in sediment traps and what the winds are doing. And I've been looking for the literature a bit and just haven't come upon it. But
Just another question.
Yeah.
Sorry. Do you guys, anybody take data in the Mediterranean Sea for this kind of thing?
Yeah, so we haven't, but other people do, and they see similar dust changes. So during the times when they get these sapropels, basically these big freshwater plumes coming out of the Nile, they get minimum dust deposition.
I don't know enough about this, but I was wondering if you have some of these other small little peaks are related to like the 8.2 Ka event, or if there's anything to the bond events or anything like that.
Trying to think if so we don't. I think that this 8.2 Ka event is this freshwater pulse into the North Atlantic related to the drainage of a glacial lake that seems to have cooled the North Atlantic and disrupted tropical precipitation with reduced strength of northern hemisphere monsoons around, as it's called, the 8.2 thousand years ago. what we see is this, and this is seen in more than one core, is this change from kind of slightly higher to minimum dust fluxes at about 8.2, but I wouldn't pound on the table about the timing of it. We just don't, there's enough smoothing there and enough H bundle uncertainty. But we don't see, the structure of the 8.2 in K event in most tropical stalagmites is kind of a down and back up, and this is just a step down, so I don't, I don't see it.
Could I, sorry,
Yep.
in the Tanganyika, did you have anything that showed, could I see that chart again?
Yeah, there it is.
Oh, okay, because I was just kind of wondering compared to like East Africa, or if it's also a latitude thing too.
Yeah, so maybe, maybe she sees it here.
Yeah, because I see it in
I'm not
Turkana,
sure.
but I wasn't sure.
Yeah,
Okay.
that's interesting.
I have two naive questions,
Yeah.
even in the danger of embarrassing myself here. How do ocean currents affect your sediment core? So I guess the ocean, I'm not an ocean guy, forgive me here, all my colleagues, but they lag behind or are before the atmosphere reaction, especially in deep ocean. And how, if you assume a similar aerosol source strength, but different current, how does that affect?
Yeah.
And my other, let's do that. Is there anything, is that a standard, is there a standard treatment for these things, or how is that counted in?
So currents move sediment, and that's one of the reasons for trying to reproduce our records, is just simply seeing, if we go back to this, you could imagine some, if you had some drastic change in ocean circulate, or in currents. I mean, that's the reason there's a hiatus here, is that somehow currents came along and blew away the sediments at that point. And so that's one reason for reproducing the records. Certainly, our thought is that the dust is falling on the surface, and it's either settling by itself or somehow forming aggregates that then sink to the seafloor. And the finest part of that can be remobilized by deep ocean currents. And then you also have the fact that ocean currents can bring in laterally more sediment to your accumulation site. Thorium normalization helps a little bit there in that in calculating the flux, you're not calculating how much sediment accumulated between two dated horizons, and you're not calculating inventory. You're just measuring the concentration of thorium-230. And the argument that's made is that this laterally transported sediment should be in equilibrium with the bottom waters and be bringing in similar concentrations of thorium-230. And so it shouldn't change your sediments thorium-230 concentration very much. And so you kind of see through that, that lateral addition to still estimate something that's a little closer to the vertical rain rate. That was also the reason for comparing the fluxes that we got for the last 2,000 years with the sediment trap data, just to kind of understand, are we roughly quantitatively accurate in terms of how much accumulation. But yeah.
Yeah, okay, so it was maybe not so naive.
No, it's a good question.
The other thing is regarding this abrupt change, I mean, that's maybe really naive now, but I looked at the American Dust Bowl.
Mm-hmm.
And if you look there, within 3 to 10 years, you have something which is green vegetated land, mesoscale, it's talking hundreds, 1,000 miles, turn into dust.
Yeah.
I mean, sand dunes which go over houses, dramatic pictures. And so, regarding your tipping point is a canoe or so, if you go from a humid to this drier section, I mean, it happened right here on this continent. Even so, we try to control it, we could not, and it went very quick. Is that something to consider? Or?
Yeah, no, and that's been one way that people have tried to explain this record, is saying, okay, you had this gradual response in the monsoon and a gradual response in vegetation, a gradual response in the monsoon and its precipitation, but vegetation and dust are things that have thresholds. They even if a constant decrease in precipitation, if you just add some noise to that record, at some point the vegetation is just going to not be able to sustain, and dust will increase. And so that's part of the reason for trying to look at other records and see, this is a river discharge record. It's something about, we think, it's something about how much fresh water is coming out of the Niger River. And so that's more of a pure precipitation record, and it shows a similar story. And then the hydrogen isotope composition recorded in these leaf waxes should also be something about precipitation amount or precipitation minus evaporation. So it suggests that it would be a simpler problem if it was just dust responding. And so this suggests that it's maybe more widespread.
One more question? All right, then I would say let's
Thanks.
thank David again for his
Daniel, remind the students about lunch, right?
yeah, of course, there's lunch served as usual in the Okubo room, and the speaker will be available from 2 to 3 to meet with students. Please take that opportunity.
But you wouldn't be able to you don't get anything.